It is insane. So, if you're more interested, that's the book Caleb was talking about, one of them, called The Emperor's New Mind. But, kind of a hard read. But let's get into today's material. Today's material, I told you last week's was probably my favorite because it's such fun material that you have terrible intuition for. And so it's so easy to just have your mind blown over and over again. This one's kind of the opposite. Today we're covering gravity. It's like the one you have the most intuition for probably, or one of the ones you have the most intuition for. But this is one of the most important lectures, historically speaking, and understanding how physics was developed throughout the past. Also, going forward, it's one of your more important ones. Oddly, for like when you get to electricity and magnetism, you make a lot of analogies going back to gravity. And we rely on your understanding of gravity to help you understand electricity and magnetism. So it's also one that in the future is made a lot of reference to help you understand new material. Trying to go back to a material that you can get a pretty good understanding of, based off of your intuition. So starting today with gravity, why Newton, one of the reasons Newton became famous, his law of gravity. Before we jump into that, let's just cover where we left off with gravity and make sure we're good with that. So first thing I want to retouch on, showed you guys this 100 times, but can't overstress it. One of our most important theorems in all of physics, the work energy theorem. What does the work energy theorem tell us? The total work gives you your change in kinetic energy, where kinetic energy is defined as 1/2 mv squared. Here's somewhat cheating derivation, just to give it to you real quick to reestablish your intuition. How did we come up with that? What was our definition of work? Work is equal to the dot product of your force vector together with your displacement vector, right? Now, your force can be thought of as mass times acceleration. Mass times acceleration, because acceleration is a derivative of velocity with respect to time. And then, because we can, we're just going to put the dt over with the dr. And what's the derivative of position with respect to time?
Velocity.
Velocity. So these two together gives you back your velocity. Pull the mass out, and then your dv is still your dv. Now integrate with respect to v. You get v squared, and then bring down your 1/2. And you get your final one minus your initial one.
Yeah, okay.
Okay, there's a quick run through of the work energy theorem, re-give you intuition for that. Because we're going to be very interested in energies at different heights, positions in space, the gravitational potential energy you have. So going back to our old way of doing gravity, what did we say? We said the force of gravity, your force of gravity is equal to mg minus sign, where g is just 9.8, some constant. And your potential energy function we define to be mgy.
Yeah.
Good so far?
Yeah.
Now, when we took work and we integrated the work done by your conservative force, in this case gravity, with respect to the direction that it's acting in our case dy, what do we get here when we integrate this? Well, m minus mg, those are just constants, pull them out. And so you're just integrating dy. What's the integral of dy?
Y.
Just y, and then evaluate at time 1 to time 2. So at time 2 minus time 1 gives you that displacement. Distribute your negative mg, which makes that one the positive, that one the negative. Now, if this is our definition of potential energy, notice that this is u sub 1.
The change in, is what you're saying?
No, here's our potential energy, mgy. So this is u for y1, so this is u1, and this is negative u2.
So it's just the change in.
Oh, sure. So u1 minus u2.
Yeah, the change in.
Kind of the change. This is the start minus the end, not the
End
minus the start.
Oh, I see what you're saying. Yeah, that's it.
So we calculated work when gravity is the only force acting. Work is equal to u1 minus u2, and work always and forever is equal to k2 minus k1. So when gravity is your only force, u1 minus u2 is equal to k2 minus k1. You can put all your 1's on that side and all your 2's on that side, and you get the equation you know and love. u1 plus k1 equals u2 plus k2.
When gravity's the only force, okay.
When gravity is the only force acting on your object.
But you can add work if it's not right.
Yeah, and then you can account for other forces through plussing work, but when we're just focusing on gravity, here's all we were doing.
Okay, yeah, I see that.
Okay, with me so far? Now, let's think for a second. Where is this equation valid?
Where gravity's the
Where?
only force.
Earth.
Earth. And not even on Earth, not even Earth, we gotta say on the surface of the Earth. Here's the universe. Here's Earth. Our equation is valid right here. It's not valid here, it's not valid here, it's not valid here. It's not even valid in the middle of the Earth. It's only valid right there on the surface of the Earth.
Well,
Where this G was a good approximation for gravity.
yeah, but G's everywhere.
Not 9.8.
It doesn't matter the number, it's just...
No, this right now is a number 9.8. It was a number measured by
Oh,
Galileo.
that's way... Well, what about on the moon? How does that change?
How do you get that on the moon? This was a number measured by Galileo. Right here on the Earth. That's what he did. That's how he got it. You want to say what would it be on the moon? You gotta go measure it on the moon, I guess.
Okay, we go measure it, but the equation...
How are we gonna go measure it? You're thinking we have now rockets where we can go to the moon and we can go measure that. Is that how we have to figure this out?
I don't know, we can do some density.
And so, we are now going to move to Newton's law of gravitation, sometimes called Newton's law of universal gravitation. Because now we're going to come up with a law for gravitational force
Everywhere.
that works everywhere. We are no longer going to say the force due to gravity is m times 9.8, or g.
It's m times m1 times m2.
Here is what Newton's law of gravity is going to say. The force due to gravity is equal to the product of the two masses divided by the distance between them squared, all times some constant.
What?
Big G there is just a constant, just some number.
Some number what? Like material density or...
It's just a constant. 6.67 times 10 to the negative 11.
Little g was that big.
Yeah, I get that. I'm just saying, where did you get that number?
So what Newton said is that the force of gravity is proportional to the product of the masses and inversely proportional to the distance between them squared. What does proportional mean? It means it's going to be that times some constant, k. Times some constant. In our case, the constant we're using is a capital letter G. And we'll talk about how we measure what that G is.
Okay, that's all I'm looking for, is how we measure it.
But G is just some constant. It's the least important part of this equation. The important part is, because G doesn't change anywhere in the universe, right? You were saying, oh, just change that G for the moon and for Mars and wherever you go, just go ahead and change your G. That's not a constant then. That's something you gotta go measure at every space in the universe. This G now is a constant. Doesn't matter if you're on the moon, doesn't matter if you're in the middle of the sun, doesn't matter if you're floating in space. The G is the G, it's just a constant.
Wouldn't the weight on Mars just be the gravitational pull at times your mass?
Yeah, but what's the gravitational pull on Mars?
How do we know it on Earth?
We measured on Earth.
So we measure on Mars.
We can't measure on Mars.
I see.
I'll give you a full decade. Okay, so this G is a constant. Doesn't change. It's the same everywhere in the universe. And it's just this number. Now here's the units on it. Notice that the units are just whatever you need to make this whole thing come out to newtons. Because it's a force. So let's see. We have kilograms and kilograms there. So we need to cancel both those out with kilograms in the bottom. We have meters and meters there. So we need to cancel those out with meters and meters in the top. And then multiply by newtons. So that's the units on it. And it's just like when you multiply by all this, it all comes out newtons per force.
Yeah, okay.
So it's very common when you come up with some equation and you get to the constant part. The constant just has a bunch of units thrown on it. And it's just the units you need to make it work out. And why is there a constant? There's a constant here because there aren't the units to use to measure the universe. Depending on what unit you choose, changes what the constant is.
Yeah, I mean, you're saying like miles to kilometers.
Yeah, if you were to just use miles, it would still be m1 times m2 divided by r squared, but you have to have a different constant there to account for whatever your new units were.
Change. Okay.
Okay, so just a constant. Now I'll give you exactly, or close to exactly, how Newton wrote his first principle. Every particle in the universe attracts every other particle with a force that is proportional to the product of the particles' masses and inversely proportional to the square of the distance between them. So here's how you encode an equation.
So you're saying every particle in the whole universe has a pull on me right now?
Yes, that is what Newton is saying. This was an absolutely astounding breakthrough. How on earth did he have this solved? that gravity is constantly pulling on everything, and that I am exerting a force of gravity on this thing right here.
Pulling it.
You know the famous story of Newton sitting underneath an apple tree and the apple falls on his head, and what is it that occurred to him? That an apple falling and the moon orbiting the earth are the same thing. And it's just gravity. It was a big mystery for a long time what actually causes things like the moon to go around the earth. What is actually happening there? Why is it going around the earth? People did consider gravity in the past, but then wouldn't the moon just fall at the earth?
It is trying to.
That doesn't really make any sense.
Yeah.
They consider somehow being electric charges are somehow responsible for the moon going around the earth. It's a big question, and Newton finally figured out the answer. No, the moon is falling towards the earth, and it is gravity. And that's all orbit is an object falling towards the earth. What happens with orbit, if you imagine, here's the earth, you build a really tall tower, and you have a really special cannon, and you load it up, and you shoot out a cannonball, what's its trajectory going to be? Well, maybe something like that. But you put even more gunpowder in there, and you load it up even more, so it shoots out with an even higher speed. Well, then it's going to be something like that. There's going to be some speed, some amount of force, some speed you could give it, so that it goes around and it comes back all the way and hits you right back in the head.
With the same velocity.
With the same velocity, not changing.
There's no friction in space.
Nothing worth measuring. It's basically a vacuum, empty. There's nothing for it to collide with.
I guess meteors would slowly erode that, but too small, I don't know.
If you were high enough up in space, then yeah.
And what's the probability that it just all sinks into place across all the universe and all the worlds?
What's the probability it
Like
sinks
that
into
they
place?
just have the perfect amount of speed? Or does it not matter, I guess?
Oh, it's not as delicate as you think. It's not easy to disrupt the system. It's hard to get the moon. You can get the moon to change its orbit. You can't get to fall to the earth.
You can't get it to fall to the earth.
No, that would take it losing a lot of energy to get all the way down to the earth.
A lot of speed.
Also mean a lot of energy, because that would take away kinetic energy. Okay, so roughly speaking, that's what orbit is, and Newton realized that's what's happening. Is the moon is traveling that way. So as it goes away from the earth, the distance between the moon and the earth increases. Right? But the earth is pulling on the moon as well. So when the moon goes over and it gets further away from the earth, well, gravity also pulled itself towards the earth. And now it gets further away but gets pulled back. It gets further away and gets pulled back. And so it's moving away from the earth at the same rate that it's falling towards the earth, making it stay in orbit. And that was his big breakthrough, or one of his big breakthroughs.
It seems very delicate.
It's not.
I don't know. And then why do things just pull together?
Why do things just pull together? Why is there a
like
gravitational attraction?
Yeah, is that like an electrical charge?
It's just a fundamental property. These are our laws. Your laws are your axioms. They're your starting points. You don't explain your laws. You observe your laws through inductive reasoning. And then you explain other things with your laws.
Based on those laws.
But you can't use the laws to explain the laws. And so the laws you just have to take for granted. You measure them, and it's just a measurable, observable fact that things behave this way. Okay. And so now, what's our definition of weight? Our definition of weight is the sum of all the gravitational forces acting on you. Right? Now let's go back onto the surface of the Earth and talk about your weight. What's your weight on the surface of the Earth?
9.81.
Huh?
9.81. What?
I'm not sure what you're saying. Your weight is just mg.
Yeah, 9.81 times G.
Oh, that's what you're saying.
Or times
G is 9.81.
Yeah.
There isn't a G for the moon and a G for Mars and a G for everything. There's just 9.81.
Yeah.
Or I think in this class 9.8. Okay, so your weight is just mass times 9.8. Using Newton's new law, what is your weight? It is your mass times the mass of the Earth. And if we're talking about your weight on the surface of the Earth, it is going to be divided by the radius of the Earth squared. That's how far away you are from the center of the Earth.
So it's all center mass.
From its center of mass. Now we're going to prove at the very end that when you have a spherical object, you can treat it as though all its mass is at the center of mass. So it's understandable that initially you take issue with that. Turns out that is the case.
Okay.
Times g. So here's your weight on the surface of the Earth. Here's your weight on the surface of the Earth. So this is equal to that.
So G is M.
So m cancels out with m. So g is equal to the mass of the Earth times g divided by the radius of the Earth squared. So you take the mass of the Earth, multiply it by g, divide by the radius of the Earth squared, and you'll get approximately 9.8, which is what that g was approximating.
So I could come up with a number between my weight on that laptop, or what my weight is to that laptop.
If it was you and the laptop out in space, and you said, I want to know what my weight is on this laptop.
Not right here. Why can't there be a weight right here?
Because your weight is the sum of all the gravitational forces. And the gravitational force from the Earth overpowers everything else.
But they're still there.
It's still there, but it's so stupid small, it's ridiculous to even talk about. Give you some rough idea. The mass of the Earth,
What? That's
the mass of the Earth is roughly 6 times 10 to the 24 kilograms.
How'd they measure that?
We'll get into how you measure that here in a second. But there's roughly the mass of the Earth. So if you think about something that even is ridiculously massive, something that's like 10 to the 18 kilograms, that's 1,000,018 times some massive object, its effect on you is still 1/1,000,000th the size of the effect of the Earth. And it's still just a rounding error when we're trying to calculate your gravity from that object. And I don't even know how to give you intuition for something that stupid large.
If that number was just one more zero on the Earth, would we all die?
If what?
If that was 25 instead of 24.
Then it'd be a lot more massive. Go ahead.
Who's the person?
Caleb.
Just Caleb.
Okay, thanks.
Okay. You're saying if this was 10 to the 23 or 10 to the 25?
Yeah.
There's other planets that have other things, and how that would have changed how life went on
Would
Earth.
kill us.
No idea. If we suddenly switch this to be a little bit lower, would that kill us? No. But over time, you would have all sorts of physiological problems, I'm sure, that rely on gravity to function the way it does. But astronauts obviously go out where they experience snow, but their bodies experience decay from not having a gravitational force acting on them. And there's ways you can fight those effects, but the point is, everything else compared to the Earth is a big nothing burger when it comes to how much gravity it produces. Okay, now, I want to say, how do we figure out the mass of the Earth? Well, first we need to talk a little bit about how we came up with this number g that we measured.
Good.
So let's talk a little bit about that. Not going to be too precise, just going to try and give you a really stupid way that you can come up with it. That's going to be a little bit far-fetched. All right, here's our stupid far-fetched way. You go into a room that's a complete vacuum, so no air, resistance, or anything like that. You take a string, and in that string, you have 2 weights of the same mass tied to either end of the string. Very delicate string, very easy to interrupt the system. If I breathe on it, it's going to start twisting.
Yeah.
So very delicate system, and you have a very delicate mirror attached right here on the system. With that very delicate mirror, we come right here and we shine a laser. So here's my laser emitter. My laser goes and it's going to hit that mirror, it's going to bounce off of that mirror, shining off somewhere else. What's the point of the laser going and hitting the mirror and shining off something else? What that's going to do is if we get any twisting in this, even teeny tiny, that mirror is going to twist a little bit, which is going to make this laser move a little bit. And the laser moving a teeny bit right here is amplified the further away you go. So then you go ridiculously far away and you see where this laser is shining. With me so far?
Yeah.
Okay, now what do? You introduce 2 big masses, so I was tugging on both of them, into the system. You bring in your boulder and you go stand next to it, and it's going to produce a teeny torque.
There's no way.
That teeny torque, you're able to measure the displacement it produces with your laser. From the displacement, you're able to get the acceleration. From the acceleration, the torque. From the torque, the force. Once you know the force, since you know all the masses and the distance between them, you can then solve for g. Okay, there's your stupid way to solve for g, but hopefully you get the theory.
How does it move it?
Very slightly.
There'd be so many other things moving it.
It's a very delicate system, moves it very slightly, and a very slight measurement with enough distance with your laser, you can capture it.
So that number's probably so far off.
Well, we now have more sophisticated ways of actually measuring this, and they're able to confirm these numbers with a ridiculous amount of accuracy. We just went over a rough idea of the first way it was ever approximated.
Dang.
Okay. Anyways, so that's how you get big G. Now, once you have big G, here's how you get the mass of the Earth. We know the gravitational acceleration on the Earth. That's something we can measure.
Mm-hmm.
Once I know G, radius of the Earth, that's real easy to calculate.
Yeah. Really easy.
Didn't they do that using like?
Radius of the Earth, it's been known since Aristotle's day. Bunch of different ways that they do it. The way they did it in his day is there happened to be a location in Greece where at a particular day of the year, a sun shined directly down a well, and so they were able to see in how much time it shifted to figure out the distance. Oh, I'm trying to remember the geometry here, or the trick here. There's a way to do it. Worst case scenario, you can go walk it off and see how the night sky changes from where you are. Walk far enough.
How does that? Okay. Yeah.
Regardless, measuring the radius of the Earth, that's really easy. Measuring the mass of the Earth, that's a beast. So before Newton, there was no good way of measuring the mass of the Earth. After Newton, measuring the mass of the Earth, now we're able to do it this way once we have big G, and that's our approximation. So that's how we get the mass of the Earth. Density of the Earth, that's real easy now. Take the mass of the Earth, since we know the radius of the Earth, we can easily calculate its volume, approximating it as a sphere. You can take the mass of the Earth and divide it by 4/3 pi, the radius of the Earth cubed, and you will get roughly 5.5 grams per centimeter cubed. To give you some intuition, water is 1 gram per centimeter cubed. That's how we define a gram, is 1 cubic centimeter of water.
The Earth is pretty dense.
On average, the Earth is 5.5 times as dense as water. Now, the density of the Earth changes drastically between the crust all the way down to the center. And I think the center, or close to the center, is supposed to be like 5 times as dense as the surface crust. So, it gets a lot more dense as you go down, but there's its average density.
Density and tungsten.
The density what?
Tungsten.
Oh, I might have. Okay, so with all that, I think we're now ready to do a couple example problems. So here's the example problem we're going to do. We're over here on mass M3, some big giant star.
Yeah.
There's another star of mass M1 here and another star of mass M1 or M2 here. This star, these two stars are 2 times 10 to the 12 meters apart. And these two stars are 2 times 10 to the 12 meters apart. We are going to calculate the gravitational force that star M1 and M2 exerts on star M3.
And an angle.
We're going to calculate the total force. So it's magnitude and the angle.
Okay.
So M1 is going to exert a force of F1, that's what I'm going to call it. M2 is going to exert a force of F2. And we're looking for F, where F is the sum of F1 and F2. Make sense?
Yeah.
Now, this is a simple problem for us. We've done these types of problems 100 times. It's just simple vector components. So what is F in the x direction going to be?
F in the x.
It's going to be F1
times
Cosine of F2.
Cosine.
F1 plus F2 times cosine of what?
Of 90.
What's this angle?
That's. Gosh. There's a way to do it. You take the length of
Rise,
that,
run.
take the,
How do the rise and the run compare?
Oh, you just take the sine of
What is the slope of that?
what? 45.
45.
Uh,
Same rise, same run. 45-degree angle.
Oh, there's your 2 times 10 to.
Oh, sorry. Right there and right there. Yes.
Yeah, I was looking for the number.
Okay, there we go. So cosine of 45 degrees. That will give us our component in the x direction. How do we get our component in the y direction?
F1 plus, or F2 plus.
Just F2 sine of 45 degrees,
And F1 doesn't have a y component.
Oh, that's a 1.
right? Once we have those, we can easily get F. What is F equal to? The square root of fx squared plus fy squared.
Oh, it's F1's track. Okay.
Right?
Yeah.
And then how do we get the angle, which we'll call theta? Theta then is going to be the arctangent of y over x.
Okay.
Good?
Yep.
All right, any point plugging those in?
That makes sense.
Okay. So there's the first problem, or the first two examples were just plug and chug examples, so I skipped 3. Okay, let's do one a little bit more interesting now. You've got some robot here on Earth. It weighs 3,430 newtons. How much would it weigh on Mars?
So we need to calculate G for Mars.
So we need to calculate G for Mars, is what I'm saying.
Wait, isn't 3,430 newtons the weight?
That's the weight of the robot on Earth.
First thing you gotta do is divide that by 9.8 to get the mass, right?
Yeah, so what's our mass of our robot going to be? Mass of robot is going to be 3,430 divided by 9.8. That will give us our mass. Once we have the mass of the robot, how do we figure out its weight on Mars?
Well, we need to figure out G on Mars first.
That's going to be the mass of the robot times
Your mass
the mass of Mars
which is given divided
times
by
big G all over the radius of Mars
squared.
squared. And those quantities were given to you in the problem.
Okay.
So,
M2, or the mass of the robot's 350.
mass of the robot's 350.
Mm-hmm.
Okay, so we can do 350 times 6.42 times 10 to the 23 times G. If you have a calculator, I strongly recommend storing G as one of your variables. And then divided by the radius of Mars squared. So divided by 3.4 times 10 to the 6 squared. And we get 1,230 newtons roughly. So a little more than 1/3 your weight. Now, maybe just point out some things really quick. Notice that the mass of Mars is about 1/10 the mass of the Earth. And yet your weight on Mars
Significantly higher.
is only about 1/3.
Are you
It
missing
has 1/10 the mass. How come your weight is at 1/10 what it would have been on Earth?
Are you missing a period there?
1, 2, 3, 0.
You weigh a lot.
3,430.
3,000.
1,230.
I only said.
Roughly 1/3. Very roughly 1/3.
Yeah.
The weight on Mars is roughly 1/3 of what it is on Earth, and yet the mass of Mars is about 1/10 the mass of the Earth.
So what other
Because
factors?
of your radius?
And it's because of your radius. Yeah, Mars is smaller, but you're closer to Mars' center of gravity than you are to Earth's center of gravity.
That makes sense, yeah.
Okay, so just some sanity checks, what you might have expected the answer to be, and what it turned out to actually be. Okay, any questions with that before we move forward?
I think we're good.
All right, so using Newton's equations a couple times, or Newton's force law a couple times, now let's talk about potential energy. So we will no longer be using mgy for your gravitational potential energy,
Oh, shoot.
because we need a whole new gravitational potential energy equation. What is our new gravitational equation, or gravitational potential energy equation going to be?
Same thing with substance.
Here's what it is. Very different. It's going to be negative your mass times the mass of whatever the big object is times g divided by r.
Okay.
That's quite different.
That's quite different.
Okay.
Now notice one thing right out the door. It's saying your potential energy is always a negative. Does that make any sense for potential energy to be negative?
No.
Unless one of your masses is negative.
And it turns out it doesn't matter if potential energy is negative, because what we care about is change in potential energy. When you were setting up some system and you were talking about this ball's potential energy, it doesn't matter if you chose 0 potential energy to be right here and you said it started out with negative 200 joules of potential energy and then went down to negative 220 joules of potential energy. All you care about is the change in its potential energy. What you call 0 doesn't matter.
So it doesn't have to be negative.
Now, what did we choose to make 0 with this definition? So in this definition, 0 is just how you set up your coordinate system. That gives you 0 potential energy, your y coordinate, right? So now we got this universal law that we want to work in all cases. Where do we want 0 potential energy to be? It's kind of weird to say, well, let's just make it like on the surface of the object. But the object doesn't really have a surface. We want to make 0 right at the center of the object where you're right there. What do we want to be 0? And so with this choice, what ends up being 0? How do I make this equation 0? R is the distance between the two objects, right?
You're saying center.
As R gets really, really, really big, what does this whole number go to?
Small.
0. So the way potential energy is defined here is it's saying 0 potential energy is when you're infinitely far away from the object. So that point clear out there at infinity, that's what we're going to call 0 potential energy. Just a choice. You got to pick somewhere to be 0. And so we're going to say 0 for all of us is the exact same. And it's that point infinitely far away. That's what we're calling 0. And so it's 0 for everyone.
That's not tangible. That's out there in infinity.
Yeah, it's out there at infinity. Or arbitrarily far. So far away that it's always a rounding error. If it's not a rounding error yet, keep going. You're not talking about the point. Once it's a rounding error, I'll accept you've reached the point. That's 0.
Okay. That's so random.
Well, it's a somewhat natural choice, because you need to find a point that no matter your problem, no matter the system you're talking about, we can agree it's 0.
So does that mean that not only does everything around us have gravitational pull currently on us, but everything in the universe does currently?
Yep.
According to Newton's law, everything in the universe is experiencing gravitational force
From everything else.
from everything else.
Every atom.
Now, when you get to general relativity, it turns out gravitational waves can actually only travel at the speed of light. This is assuming instantaneous interactions.
Gravity only travels at the speed of light.
If we're going to say it travels, yeah, gravitational waves move out at the speed of light.
Everything's being traveled.
If the sun suddenly ceased to exist, the Earth would not instantly start flying off its orbit. It wouldn't be until we saw the sun was gone that the Earth would then start taking off from its orbit. In the meantime, it would keep orbiting as though the sun were there.
So why does gravity have a time?
Because it does. But for the purposes of our class, it doesn't. It's instantaneous. We're sticking with Newton. Yes.
Yep,
Einstein is not intuitive. It is very strange. But sticking with Newton so far.
So not a lot. Okay, not everything does.
So now, this is going to be our definition, but now let's calculate the work done by the force of gravity. Same exact thing we did over here. When we calculate the work done by the force of gravity, we got our potential energy equations. We're going to do the same thing. So we're going to do the work done by the force of gravity going in some direction dr, radially outward from whatever object you're talking about.
Well, the constants is the same equation.
And we're going to say that the force is pulling you towards the Earth. You can think about big M here is the Earth, little m is you. And you're floating out there in space.
Okay.
And just a picture you can have in your head to help with intuition.
Oh.
And dr, this is along the path that you're going to plummet to the Earth along.
Okay.
Okay, so got the intuition? All right, let's integrate this. Now notice, everything here is a constant except for the r's.
Yeah.
Your mass isn't changing, the mass of the Earth isn't changing, and g is obviously a constant. So pull all those out, and so you just have dr over r squared. R squared in the denominator is the same thing as r to the negative 2 in the numerator, to help you integrate it. You remember how to integrate now?
Yeah.
Add 1 and divide. So negative 2 plus 1 is?
1.
Negative 1. So it's going to be r to the negative 1. And then you divide by negative 1. Dividing by that negative 1 is going to cancel out with that negative out there.
What? Oh, so you just pull it out, right?
Yeah, dividing by negative 1 and times it by negative 1 is the same thing.
Yeah. What? You're moving it across.
When I integrate r to negative 2, I am going to get negative r to the negative 1.
Yes.
Okay, so that's what this is going to turn into.
Well, divided by -1.
Well, that's why I put that negative sign there. Dividing by -1 and multiplying by -1 are the same thing.
Okay, I did not know that.
Okay, so now pull out our negative sign to cancel out with that one. So mg,
Okay.
and r to negative 1 is the same thing as 1 over r.
Yeah.
And evaluate for your two endpoints, r2 minus r1.
Yeah, makes sense.
So you follow all that? Now here's our definition of potential energy. So little m times big M times g, all times negative all over r1. When I distribute that in, this is going to give me that. And when I distribute this to this, it gives me that.
Oh,
Just distributing it through.
yeah, I see that. I see.
Okay. Now if you see that, notice negative m times big M times g all over r1. This is exactly what u sub 1 is going to represent.
Shouldn't it be flipped then?
Yeah, so I took the second one and I wrote it first.
Well, it has to be negative.
No, u is negative this. So here's u
Yeah.
for r1. So here it is, u sub 1.
So it's still.
Meaning u when you plug in r1 for r. Now we need to subtract a negative because that's positive. So that's going to be subtract negative m times big M times g over r2. You follow that?
I see the twist.
And so once again you get u1 minus u2, which is exactly what you got over here, u1 minus u2, which is different potential energy formula. And so if work is equal to u1 minus u2, and work always and forever is equal to your change in kinetic energy, K2
U1 minus U2
minus K1.
K2 minus
now you can move your 1s to the same side and your 2s to the other side. And so you can still use this formula the way you know and love. I told you, you're going to use this formula a billion times, never going to go away.
Still do.
So, still works with everything we're doing with gravity. Once again, it's just this is our new potential energy function. And this is our new force function.
Force.
This is a force of gravity now,
Force
not
of
mg.
gravity. Okay.
This is a potential energy of gravity now, not
mgy.
mgy.
Then G's an accelerator, right?
G gives you an acceleration the same way that 1m times big G over r squared gives you an acceleration.
Okay.
Because all that's left is a mass, and together they give you a force.
Force, which does that mean?
So everything except for one of those masses gives you an acceleration. So you can calculate the acceleration you have on the Earth, how you accelerate towards the Earth, which is a g, or we can calculate how the Earth accelerates towards you if you want, which would be so ridiculously small. It's
Okay.
because when you are falling towards the Earth is also falling towards you.
Just not really.
Just so ridiculously small, it's absurd to talk about. Because how you fall towards each other is going to be proportional to your masses, and your mass compared to that mass is nothing. Right?
Yeah.
Okay. So now let's talk about
Aren't we included in that mass?
if I remove your portion of it, it doesn't change anything.
I'm saying that's how they calculated it based on those.
It is, the rounding error on it is going to be plus or minus way more than the entire human race. So you have no effect on that number.
Interesting.
Okay.
And what's the sun relative to that number?
The sun I think is roughly 10 to the 30. 2 times 10 to the 30 is what's coming to my mind. Could be remembering it wrong. We'll get to the sun somewhere along through that.
Oh.
But on the order of magnitude of 1,000,000 times the size, I think is roughly right. Could be wrong. We'll see. Anyways, now our next question, that's a gravity question. I have this piece of chalk, and I throw it up in the air. As I throw it up in the air, gravity's pulling it back down.
Yeah.
But the higher it goes, the less gravity's pulling on it.
True.
but gravity's always pulling on it.
True.
We're using Newton once again, so even if I throw this, even
Like-
as it goes through space, even when it's a trillion miles away,
Yeah.
doesn't matter how far, gravity's still going.
So we're doing.
Doesn't matter how fast it's moving.
Yeah.
So the question is, how fast would I have to throw this piece of chalk so that it would never come back to the Earth?
Isn't that?
We're assuming Newton, so it's always pulling on it. So even if I throw it faster than the speed of light, gravity's still pulling on it no matter what. Can't get rid of gravity. How much speed do I have to give this piece of chalk so it would never come back to the Earth again? Gone forever. Ignoring air resistance
So you're
and
finding the minimal
everything else.
value. The minimal value of any velocity is what?
it's
0?
called the escape velocity. How much velocity do I need to give this to make it escape the gravitational pull of the Earth?
minimum.
Yeah, what's the minimum velocity I could give this so it would never come back to the Earth?
When you set your final velocity to 0 and use a kinematic.
Well, we'll go through how to set it up, but think about how weird that is, because gravity's always pulling on it. Doesn't that mean, no matter how fast I throw it, eventually gravity's going to slow down more and more and more and more, and eventually it's going to fall back to the Earth with enough time?
No, because the numbers, as you go out, it's going to shrink. How much it's affecting.
But even if it shrinks, it's still always slowing it down. More and more and more.
Not enough to matter.
Not enough to matter. Even with an infinite amount of time slowing it down.
Well, then it would.
So we'll give it an infinite amount of time.
But there's other things in the universe pulling it out.
Pretend that it's just this piece of chalk,
Okay.
the Earth, and I throw it. Is there a speed that I can give it so I will never come back to the Earth?
No.
Because the Earth is always slowing it down.
Assuming.
And eventually it has to come back to the Earth, right?
Assuming that.
And the answer is no, it does not eventually have to come back to the Earth. And it's exactly the intuition you had, is because gravity is pulling on it less and less. So yes, it's always slowing it down,
But not.
but
They got-
it's always slowing it down less and less. It's kind of like saying, let's say after 1 second, let's say that gravity, we initially give it a speed of 1. We'll say after 1 second, gravity cuts that in half, 1/2. Well, now it's further away, so gravity's not slowing it down as much. And so let's say in the next second, gravity halves it again. So now it has 1/4 its speed. And in the next second, gravity halves it again, and now it has 1/8 its speed.
Sounds like
And then
it's
1/16,
worse.
1/32. If we kept following that pattern, just halving it,
that'd
you're
be
never
bad.
going to get to 0. Or in the limit, you get to 0 and it stops. You don't get it going negative and falling back to the Earth.
So it's not like this, it all adds up to 1.
Well, it is kind of like that. If we were adding all these up, then this would all add up to 2. It wouldn't add up to infinity. It's the same concept.
How? It's half every time.
Okay, if we did this, then that would come out to 2. It's a similar concept where an infinite sum doesn't necessarily mean infinity. So even though it slows down my piece of chalk an infinite number of times, that doesn't necessarily mean it reverses the direction of the chalk.
It's got to pull it back though, so it will at some point.
No. And so we'll calculate that.
What's different between this and
It's the same concept. The fact that this doesn't go off to infinity, it just gets closer and closer to 2. Or if you keep halving, it doesn't eventually become negative. If I keep halving my speed, it doesn't eventually become negative. My speed just eventually becomes 0 in
but
infinity.
It will cross over at some point, won't it?
After infinity.
It will
So
cross over.
it will cross over after infinity. So get through infinity, then after that. That's where it crosses
I
over.
don't, okay.
You're right. I don't either because you're not getting past infinity. Getting to infinity, that's as far as we can go. All right. So putting infinity as a limit to how far we can go, it will get to 0 in that one particular scenario. So it should bother you a little bit when you first think about it that shouldn't it always come back to the Earth? And then the answer is going to turn out to be no. And it might be a little bit surprising to you how small the velocity is you need to give this piece of chalk for it to never come back to the Earth. When we calculate it, I'll give it to you just coming up. It's 1.12 times 10 to the 4 meters per second.
10 to the 4.
Yeah. So we're looking at roughly 11,000 meters per second. Now that's still really fast, but nowhere close to something like the speed
What's
of
a
light.
gun shoot?
Huh?
Does a gun shoot close to that?
A gun
A
shoots
sniper.
hundreds of meters per second, thousands of meters per second. Maybe there, probably some, yeah. I don't know.
So there's some guns that can shoot a bullet outside.
Well, there's air resistance and all that now.
Oh. Yeah, say goodbye.
So
So it's not simple. It's not a little bit. Yeah, okay.
Okay, but yeah, ignoring air resistance, you're trying to figure out how fast do I got to get a rocket so it gets off the Earth and doesn't come back. Here's the speed you're looking for. Make sense?
Yeah.
Okay, so now let's actually see how we calculate this. So our escape velocity, once again, we're going to use the equation we know and love. Your initial potential energy plus your initial potential plus initial kinetic equals final potential plus final kinetic. Right? Now we're starting out with our piece of chalk. Where are we starting with it?
0.
Not 0. Where does it start? Where is this? On the surface of the Earth. What's the potential energy on the surface of the Earth relative to the Earth?
Oh yeah, because 0 is infinity.
So it's going to be the mass of this thing times the mass of the Earth times g all over the radius of the Earth.
The 0 radius though.
On the surface.
Wait.
I am not at the center of the Earth. I'm on the surface of the Earth. How far away am I from the center of the Earth?
Okay.
The radius of the Earth.
Yeah.
So here's the potential energy for our chalk. Good?
Yeah.
We're trying to figure out how much kinetic energy I got to give it. So we're going to solve for this velocity.
Okay.
So I'm going to give it some initial kinetic energy, I don't know. Now, let's say our final potential energy. Where does our piece of chalk end up?
In space.
After infinity.
After infinity 2.
Infinite.
It ends up at infinitely far away. Or in other words, its potential energy is at infinite far away. What's our potential energy?
0.
0.
After infinity it's 0, which is never gonna happen.
Well, not after, at.
It's never gonna happen.
And then what is our final kinetic energy? If I am trying to find the minimum speed to make sure it never comes back to the Earth, I want at infinity it to have 0 kinetic energy. I don't want it to have any left over. I want to throw it a little bit harder than I need it to. I want the minimum. So we want our final kinetic energy to be 0.
So
our final potential energy is 0 and our final kinetic energy is 0. So we get 0.
That's it. Just okay.
Initial potential energy plus initial kinetic energy equals final potential energy plus final kinetic energy.
Yeah.
Okay. Now we're just solving for v. So move this to the other side
Yeah.
and multiply both sides by 2.
To get yeah.
Oh, sorry. First thing I should have said, divide the m's out. You can move it over, then divide the m's out if it's easier for you to see that. Notice that the mass goes out. So it doesn't matter if I'm throwing this piece of chalk or if I'm throwing a rocket ship. I got to get it going the same speed to make it escape. Obviously, you got to give the rocket way more energy because it's way more massive, but give them the same speed to make the escape velocity. So we get v squared is equal to that. Take the square root of both sides, and that gives you the escape velocity for any object you were on. This works if you want that to be the mass of Jupiter and the radius of Jupiter, the mass of the sun and the radius of the sun. Nothing here is special about the Earth. In the special case where you plug in the mass of the Earth and the radius of the Earth, you get this particular number. Good?
Yep.
Okay, now let's do an example problem. This time what the author wanted us to do was to take our piece of chalk or a ball, and I'm starting out on the surface of the Earth, and I want to throw it up so it achieves a height as high as the radius of the Earth above the surface of the Earth. So what's the radius of our Earth? It's roughly, it's written up here somewhere. Is it not? The radius of the Earth, roughly 6 million meters, if I remember right. Can't believe I don't have it written. Let me check my calculator. Radius of the Earth. Okay, 6.371 times 10 to 6. Let me just put that up here somewhere. 6.371 times 10 to 6. So yeah, roughly 6 millimeters. Okay, so I got this piece of chalk. How fast do I have to throw it so that it goes another 6.371 million meters above the surface of the Earth?
Gravitation. Gravitational pull. I don't know.
Well, how fast do I have to throw it? If I want to go off to infinity, I have to throw it this fast. This time I don't want to go off to infinity. I just want to go this high above the Earth, and then it can fall back down. You see what I'm saying?
Yeah.
Right, so here's the Earth. Before, we were seeing how hard I have to throw the chuck so it keeps going off forever. This time I want to know how hard do I have to throw so it goes up to here, then falls back down.
Yeah.
Goes up the radius of the Earth into the air, falls back down. That's what we're solving. Okay, understand the problem. Now let's set it up. Once again, we use the equation we know and love. Initial potential energy plus initial kinetic energy equals final potential plus final kinetic.
Yeah.
What is our initial potential energy?
0.
No.
Oh wait, it's
0 is infinitely far away. It is negative the mass of whatever our object is, the mass of my chalk,
times your mass of Earth
times the mass of the Earth
divided by R
times G divided by the radius of the Earth, not squared.
Yeah.
Squared gives you
The actual G.
your force.
Yeah. It gives you.
Okay. So here's your initial potential energy plus your initial kinetic energy. We don't know what that is. That's what we're solving for, right? We need to figure out the velocity. What's our final kinetic energy going to be?
0. Oh, kinetic?
Our final potential. Did I say kinetic?
Yeah, you should.
Sorry. Our final kinetic energy is going to be 0. Our final potential energy is going to be when it's 2 radiuses of the Earth
It's
up.
going to be that, but 2 RE, right?
It's just going to be this same thing, but 2 RE in the denominator.
2 RE.
2 radiuses of the Earth. So it's just going to be negative m times the mass of the Earth times G. Sorry, mass of the Earth times G. All over 2 radiuses of the Earth. That all make sense?
Yep.
Okay, first thing I'm going to do is divide out the mass. So notice that the mass of the object I'm throwing, it doesn't matter for how much speed I have to give it to make it go that high.
Which is makes sense.
Okay. Now I'm going to add this to the other side.
Then you're wiping the whole.
This
out.
is one of these. This is half of whatever this is. If I have half of one and I plus a whole one, what do I get? A half of one. So now I get 1/2 v squared, because that went out, is equal to positive mass of the Earth times G all over 2 times the radius of the Earth.
So you can just get rid of your 2 and then square root.
Multiply both sides by 2. Good. And then take the square root. Hopefully you're okay with my erasing. You follow all of it?
Yeah.
Where did the RE from the first left-hand side of the equation go?
He moved it over.
I added this same term to both sides. Because those are the exact same term. This is just half of that.
Okay.
And so we were left with positive 1/2 of them.
Yeah, that makes sense.
And then cancel out the 2, took the square root, here it comes. And so notice that that velocity, it's the same as your escape velocity, just without the 2 there. And so when we actually calculate that, let's plug it into our calculator. So we're going to take the square root of, we have the mass of the Earth times G
Would it be like
divided by the radius of the Earth.
400 meters a second?
It's going to be 5.6 times 10 to the 3 meters per second.
And we get 7.9 times 10 to the 3.
700.
Yeah.
800.
So this is going to take roughly, it's going to take the square root of 2 as much as this, because if you were to take that 2 out, that would just be the square root of 2 and then the same number.
Yeah.
So notice that 11,000 gets you to infinity. 8,000 barely gets you the radius of the Earth up in the air.
So once you get...
So almost all of it is just going to get past that first little bit above the Earth.
Yeah.
Because the gravitational pull of the Earth dies off at r squared. If I go twice as far away from the Earth, I'm experiencing 1/4 the gravity.
Yeah. That makes sense.
Okay. So with that, let's move the camera. and now start talking about orbits.
Oh, fun.
You sound excited.
I'm excited.
Well, sucks Caleb missed this lesson. Seems like his jam. His cup of tea, you know.
Yeah, not a good one to miss. Okay. Circular orbits. We've already talked about circular motion. When we have an object traveling in uniform circular motion, what has to be happening? So you can think about I'm spinning a ball on a string. How do I keep it in uniform circular motion? I'm exerting a force in the tension of the string to create a centripetal force.
There has to be a force towards the center and a force tangent to it.
No, there's a force towards the center creating the centripetal acceleration. If it's also speeding up as it goes around, then you have to have a tangential force. But if it's not speeding up, so it's just uniform circular motion, your force is just creating centripetal acceleration, and that's did we call it centripetal? This book calls it something. Was it radial that they called it?
Centripetal
I thought it was
force.
centripetal.
Sounds right.
Centripetal, whatever it was. But here was the equation we used. Omega squared times r, or v squared over r. And we've seen both those a few times for uniform circular motion.
Yeah.
That's the acceleration. And so your force has to produce this acceleration if it's going to keep an object moving in uniform circular motion.
Yeah.
So we are going to start out by assuming that our orbit, we're going to start with circular orbits. And we're going to assume that these objects traveling in circular orbits are traveling in uniform circular motion. They're not speeding up or slowing down, which is a pretty good approximation for things like the moon and the planets around the sun, or at least the inside planets around the sun.
Yeah.
So, here we have our moon with mass little m. Here we have the Earth with mass big M. And the moon is traveling around the Earth with uniform circular motion. Or some satellite around the Earth, doesn't matter. We'll just pretend the moon for now for a picture in our head.
Yeah.
With me so far? So then the force of gravity between the Earth and the moon is going to be
Consistent.
equal to the mass times the acceleration of the moon.
Yeah.
And that's also going to be equal to what Newton's equation he gives us. The mass of the moon times the mass of the Earth times g divided by the distance between them squared.
Times your acceleration.
Well, no. Force is equal to mass times acceleration. And the force of gravity is also equal to this.
Force of gravity.
Force of gravity.
Okay.
So, if gravity is the only force acting on the moon, which it's good enough to say it is, then the mass times the acceleration of the moon is going to be equal to the mass of the moon times the mass of the Earth times g divided by r squared. Because that's the only force acting on it. Divide little m out on both sides.
You can do that.
Yeah, to get the acceleration of the moon.
Okay. Yeah, that makes sense.
And so the acceleration of the moon is going to be equal to big M times g over r squared. But the acceleration of the moon, the only acceleration acting on it is its centripetal acceleration.
Which
So
holds it.
I'm going to replace that A with the A for centripetal acceleration. And then this is still just right there. Then we can cancel out the m's on both sides and multiply both sides by r. What I'm trying to figure out is how fast the moon is moving around the Earth. The velocity of its orbit.
Okay.
So that's the first thing I'm solving for. Sorry, I didn't say anything about that, did I?
No, it makes sense.
So whether it's the moon going around the Earth or some satellite that Elon Musk put up into
Doesn't
the
matter.
orbiting around, here's how you would calculate how fast it's moving. If it's moving in uniform circular motion, this is true, which gets us to here. Cancel out the m, multiply both sides by r, gets you to here. Take the square root of both sides, that gives you the velocity.
Okay.
So if you want to orbit at some particular height above the Earth, if that's the mass of the Earth, and you want to orbit at some particular height around the Earth, here's the velocity you need.
Gosh.
So now let's try another question. There is a velocity I should be able to throw this piece of chalk with, assuming that the Earth was perfectly flat. Perfect sphere. There should be some speed I could throw this chalk with so it came around and hit me in the back of the head. Should be possible.
Yeah.
That would be its orbiting velocity.
Orbital velocity. So it's that.
Well, let's calculate that one. Let's see, what did I calculate here? 2 races of the Earth. So for this one, I calculated if you went the radius of the Earth up into the sky and were to release a satellite, then here's how fast it would have to be moving.
Yeah, okay.
5,600 meters per second, roughly. If I were to take this piece of chalk now and chuck it, let's calculate that one really quick.
So 3 meters, well, don't you have to know the radius of plus 3? Which doesn't really matter. So you just take the radius.
So, oh, that's surprising. I didn't even think about that. So now if I want to know, I grab my piece of chalk now, and I chuck it that way. How fast would I have to throw it so that it started orbiting? So then we would plug in the mass of the Earth times g times the radius of the Earth, because I'm trying to get it to orbit at the radius of the Earth's height above the Earth, above the center of the Earth. Sorry.
The one at Earth's height?
The one at Earth's height above the center of the Earth. Remember, your R here is from the center of the Earth.
Yeah, so you're just trying to find surface level.
Yeah,
What's your R?
radius of the Earth.
Well, okay.
This is the radius of the Earth above the surface of the Earth.
Yeah, I'm just asking where.
If I got rid of the 2 there, then that would be just
the
me
surface.
throwing the piece of chalk at the surface of the Earth,
Yeah.
trying to get to orbit. And if I did that, well, that turns out to be exactly what we calculated right here, which it would come out to roughly 8,000 meters per second. So that's how fast I'd have to throw it to get it orbiting here. The higher up I go, the less speed I need in order to get it to orbit.
Oh, is that what you're saying was interesting?
It was interesting that that came out to that exact thing. I didn't think about that.
Okay, that makes sense.
Okay, so that is its velocity. That's how you calculate the velocity. If you want to calculate the velocity of the moon, all we would need to know is the distance to the moon. And then we can calculate the velocity of the moon. Since we already know the mass of the Earth and g.
Yeah, that makes sense.
So another thing we could do now is calculate period. How long it takes something to go around. So let's do that, but this time we'll do it for the Earth and the Sun.
Okay.
Now going back to uniform circular motion, what is period? Period is how long it takes you to complete one full orbit, to go 2 pi radians. So, maybe should have started by writing it this way. Omega times period is equal to 2 pi. If omega is how many radians per second you're going, and your period is how long it takes to go 2 pi, then your rate times your time gives you your total distance.
Yeah, that helps.
Okay, so now just resolve that for period. Period is just 2 pi over omega.
Yeah. And you're trying to get it.
Now, I don't know if you remember this. What is V? It's omega R.
Yeah, I remember.
Or solving for omega, omega is V over R. So replace omega with V over R. R in the downstairs. Downstairs of the downstairs goes upstairs.
Okay.
So that's how we get here. And now we already figured out the velocity of orbit. That's right here. So plug in that for velocity. So just plug in the reciprocal of this, because it's in the downstairs. And here is your period. Last thing we can do is square root of r is the same thing as r to the 1/2. So r to the 1/2 and r to the 1 gives you r to the 3/2. And then keep the square root in the bottom still.
So you took out the square root. Oh, yeah.
And so there you go. There is your period. If you know how far away your satellite is that you're talking about, you can talk about how fast its period will be. So, to give you an example, here's the equation all boxed up nice for us so that we can make reference to it as needed. But if we were talking about the period of the Earth around the Sun, how would I calculate that? I would do 2 pi times 1 AU. An AU is an astronomical unit. It's the distance from the Earth to the Sun.
1 AU.
Yeah,
So it's just what they said as.
yeah. They defined 1 AU to be the distance from the Earth to the Sun, and you can convert that to meters. It's just a unit. So, roughly 93 million miles. So 2 pi times 1 AU to the 3/2, and then divide that by the square root of the mass of the Sun times g. And then if you convert it, that will give it to you. If you convert that to meters and then plug it in, that will give it to you in seconds. And then you can convert that to days, and you'll get roughly 365 days. I think it came out to closer to 365.5 days with our rounding errors.
Do we know Earth's velocity?
You can calculate Earth's velocity with this. You take the mass of the sun times g divided by 1 astronomical unit all under the radical. And that will give you the velocity of the Earth going around the sun.
I wonder what that number is.
Well, you can plug it in later. All you need to do is replace r there with an astronomical unit, m there with the mass of the sun. Easy enough to do. Okay. So, there is your speed and your period when you are going in circular orbit and moving in uniform circular motion. Good?
Mm-hmm.
Last thing I want to talk about is the energy of circular orbit. Now, when you're in circular orbit, your energy is not changing. Your potential energy is not changing. Your kinetic energy is not changing. You're not speeding up. You're not slowing down. You're not getting closer. If you think about you orbiting the Earth, you're not getting closer to the Earth or further away from the Earth. It's all constant. So whatever your potential energy plus your kinetic energy is, has to be a constant.
Okay.
It's not changing as you're orbiting the Earth. Make sense?
Mm-hmm.
And so whatever that energy is going to be equal to your potential energy plus your kinetic energy. Now, what is your potential energy if you're orbiting at some distance r from the center of mass? It's just your potential energy. So that's just what it always was. But now we can do your kinetic energy. We can do 1/2 mv squared.
And that's the V of the Earth.
And that's v of orbit. We're talking about your energy when you're orbiting. So this will be your velocity when you orbit. So now we can talk about your total energy when you're in orbit.
Okay, that makes sense.
Okay. Now, when you square a square root, it just undoes it. And so it's just going to be 1/2 m times big M times g over r.
Yeah.
So we have negative m times big M times g over r plus 1/2 m times mg all over r, which leaves us negative 1/2. I have negative one of them plus 1/2 gives me negative 1/2 of them.
Yeah.
So there is your total energy of orbit. How much energy you have if you are orbiting an object at some radius r. If I just know how far away you are orbiting, I can then figure out how much energy you must have.
And what is energy?
A scalar.
What unit is that?
Joules.
Okay. That makes sense.
Okay, so this will give you your energy in joules. Okay, so let's try one. We want to put a 1,000 kilogram satellite into orbit, 300 kilometers above the Earth. So that's our job. Here we are, we're going to get to work on it.
So we need to get it to escape velocity?
Yeah, so first, once we get into orbit, we're going to figure out what velocity will it have, what will its period be, and what will the centripetal acceleration acting on the satellite be. Because it's going to be in orbit now, so it's going to have centripetal acceleration.
Yeah.
Okay, so first off, let's assume we got the satellite up into space, and let's figure out what that velocity is going to be. So what will be the velocity of our satellite if it is 300 kilometers above the Earth?
Square root of mg divided by 300 kilometers.
Square root of our m in this particular case is mass of the Earth.
So me times g divided by 300 times r. Right?
300 times r. This is 300 kilometers.
Yeah, times r.
Now, it's going to be the radius of the Earth plus 3 times 10 to the 5 meters.
What?
That's how high above the center of mass of the Earth we're making it orbit.
Yeah, 300 above r. Oh, so they're not times. Yeah, you're right.
300 kilometers. Convert to
Yeah,
meters,
I
always
did.
and forever.
I thought they were multiplying, but yeah.
Okay, so 3 times 10 to the 5 meters
Added.
above the radius of the Earth is how high up it's going to be from the Earth's center of mass.
Yeah.
Okay, so there is our velocity, and now you could just plug in the numbers that we have. So, what will this be? So, mass of the Earth times g divided by re plus 3 times 10 to the 5. It's going to be approximately 7.6 7.3. Not sure how many significant figures we had. I'm guessing 3. Times 10 to the 4 meters per second. Okay, so that is how fast that satellite would be moving out in space. What would its period be?
Calculated by 2 pi over omega equals.
So that would be this one. So we would be doing 2 times pi times
r
this distance, RE plus
to the 3 halves.
3 times 10 to the 5 to the 3 halves, all over
Pi root mg.
square root of mass of the Earth times g.
G meaning not gravitation.
G not meaning gravity, G meaning 6.67 times 10 to the negative 11. Okay, so let's see what we get when we do that. So we're doing 2 pi times radius of the Earth plus
40 days.
3 times 10 to the 5, all to the 3 halves, divided by
Square root
the square root
of
the mass of the Earth,
times g.
mass of the Earth times g. And I'm getting 5,422. That is fast. Divided by 3,600. That's 1.5 hours. Hope I did that right.
That is
What example are we on? I didn't label it.
like third.
No, because I skipped a couple. We did the weight of the robot. Let's see. Has to be here. Satellite. Velocity. 7,720 meters per second. They have a rounding error that made it slightly different from us. I have more exact values plugged in for the mass of the Earth than what they used in my calculator. For period, 90.6 minutes. Which I did it in hours, 1.5 hours, but so basically the same thing.
That is insane. So Elon Musk satellite passes every 1.5 hours.
If it's that high, yep. Apparently. That's nuts.
That is insane.
That's faster than I anticipated. Okay.
Way faster. I thought it'd be like a couple days at least.
Let's see, centripetal acceleration. We'll kind of skip that one and just go straight to total work. I think this is one we care the most about.
Do AC?
Oh, centripetal. You take just this, v squared over however high it is.
Oh.
And we already have the v and then the r.
Yeah.
Okay. So, yeah, that's how you do it. And then,
That's
more interesting, how much work do we have to do to get the satellite up there? I think that's what we care about.
Yeah, so work is U initial
So-
minus U final.
Work is a change in the system. So our initial potential energy, U1, plus our initial kinetic energy, what's the initial kinetic energy of the satellite?
0.
0. Plus the work we put into the system.
Which is
That's what we're solving for.
friction is what we're asking. Or what?
We're ignoring friction. Just literally ignoring air resistance, ignoring friction. You got the satellite here. How much energy would it take to get it up in space and get it moving fast enough that it orbits?
What would your work be? Work beyond the system to pull it out. I get you.
Imagine that you actually did this. You had a really tall ladder that went all the way up to space. And you're going to grab that satellite and you're going to climb that ladder, lifting it up in space. And once you get up there, you're going to take that satellite and you're going to chuck it fast enough. That's one way you can think about it. Superman doing this. How much work would that be? How much energy would that require? How many joules?
Lots.
Okay, so U1 plus the work that goes into the system
Yeah.
is equal to U2 plus K2.
Or U.
But we already found in orbit that your energy, total energy, will always just be this. So we can skip straight to, this is going to be equal to negative m times big M times G all over 2 times R, where R is however high up you're getting it.
And U is 0 then, right?
Well, we already calculated that when you have an object in orbit, its potential energy plus its kinetic energy is equal to this. So this is U2 plus K2. It would come out to this if we did it again.
Okay.
We don't need to do it again because it'd be that same math.
Yeah.
So here's what it always is.
Yeah, makes sense. Okay.
Okay, so now our work that we do will be equal to the final energy, negative m times big M times g over 2r
Minus U1.
minus u1. Now what is u1? It's the potential energy on Earth. It's negative m, little m times big M times g over r, where r is the radius of the Earth.
So it's just half.
When I move u1 to the other side, it's going to become plus. So this is going to be plus
So it's just half that.
little m times big M times g
It's what we already did.
all over 2, almost. This r is the radius of the Earth. Radius of the Earth. This is our radius of our orbit.
Oh, shoot.
This is that plus that. This is just the radius of the Earth.
So it would just come.
We'll have to plug it in. There's not an easy way to just see what it will be. You have to plug it in, because that r and that r are very different.
Well, they're only different by a factor of 300 kilometers.
Yeah, you're right. So I'm going to factor that out, and I'm just going to do, I'll factor out the little m, big M, and g over 2, and just do 1 over the Earth's radius minus 1 over the new radius, and then multiply it by all that. So we'll do 1 divided by the radius of the Earth. Oh, I'm going to need parentheses around all this. Sorry. 1 divided by the radius of the Earth minus 1 divided by the radius of the Earth plus 3 times 10 to the 5. So the radius of the Earth plus 3 times 10 to the 5. I'm going to take that whole thing and multiply it by everything we factored out. What did we factor out? We factored out the 1/2. We factored out the mass of the rocket, which is 1,000, not 10,000. Make sure I did that right. And we factored out the mass of the Earth. And we factored out g. Did I do all that correctly?
Sounds right if you put values in. It'd be the obscene amount of work.
Sugar. I had a parenthesis in the wrong spot. Okay, 1.4 times 10 to the 9. Joules is what I'm getting.
I'll try.
3.26 times 10 to the 10.
That's not good.
That is not right.
Maybe your formula's right, you just plugged in.
Yeah, I plugged in something wrong.
So their thing looks the same. They're running up.
Is that times 6 or times g?
That's a G. Alright, let's see what I plugged in here. I did 1 divided by the radius of the Earth minus 1 divided by r, which is the radius of the Earth, plus 3 times 10 to the 5. Is that right?
3 times 10 to the 5.
3 times 10 to the 5
Oh.
times 1/2 times 1,000 times the mass of the Earth times g.
Just do it.
And I'm still getting the same thing. Alright, let's break this up into one piece at a time. Let's calculate this and make sure we're getting the same number as the author to make sure I'm not making any small mistakes. So calculating just the energy in gravity, we should have our mass, which is 1,000, times the mass of the Earth
Math, what math? Oh, yeah.
times G. Where's my G?
Mass of the Earth, where's that?
I don't know, I just have it in my calculator.
Oh.
There's one right there. Times G divided by 2 times the radius of the Earth. Negative 3.12 times 10 to the 10. They get negative 2.98 times 10 to the 10. That could be simply because I have a more accurate number for G and the mass of the Earth. So got the same for that. So for this, I got approximately minus 3.13 times 10 to the 10. And now, okay, so that's what this comes out to. So now U1, and then work will be the difference between them. For U1, that is going to be equal to, right here, that will be the mass of our object, 1,000, times the mass of the Earth times G divided by, oh my goodness, there isn't a 2 on this one. The potential energy on the surface of the Earth is just that.
You didn't say there was a 2 in your writing.
Yeah, but I just wrote it.
You
Okay,
that's what I said.
there's my mistake.
Are you
Okay.
sure?
Yes.
That's so far into the equation.
Divided by RE equals
That's only half of the equation.
that. Now if we do this minus that, we should get roughly 3.1 times 10 to the 10. And they round a little bit different, 3.26 times 10 to the 10. Okay, so yes, that's right. That was a mistake. Sorry about that.
I'm gonna finish.
Okay, now on to the more fun stuff. Should we take a quick break before Kepler's laws? Let's take a break before Kepler's laws. And then we'll continue from there. Something. All right, let's get to one of our more fascinating people in history, and maybe a little bit of a story. So Kepler comes right after Copernicus. Well, put 3 people in order: Copernicus, Galileo, Kepler, Newton. Putting them in chronological order. What's Copernicus famous for?
Copernicus is something famous.
Was he the model?
How much of the whiteboard do I have?
Copernicus.
Give me a little. Yeah, what did Copernicus say? Copernicus said that you have the sun and the planets travel in circles around the sun.
Yeah, heliocentric, right?
Heliocentric model. Or sun-centric model.
Oh,
Say it
so
with
it's
a
the
little less
center of
Greek.
the universe.
That the sun is what's at the
Center
center.
of the galaxy.
The galaxy universe. I guess they know.
Well, that the planets go around the sun. Not that the sun goes around any of the planets. All the planets go together around the sun.
I used to believe everything went around the Earth.
Which is already kind of an amazing thing to say, that this is the way everything is working. It's easy enough to say if you could somehow look down on our solar system from a bird's eye view, But to make that determination while you're standing on this rock going around everything is quite a thing to say, especially since this rock at the same time is also spinning around like that every 24 hours as it's traveling around here.
Yeah, that's quite remarkable.
So it's quite remarkable. He put off publishing for a while, thinking that he might be ridiculed, because who would believe their lying eyes? You can go outside and you can literally watch the sun move around the earth. What are you talking about that the earth moves around the sun? So Kepler, or Copernicus, you're telling me the moon moves around the sun, but the moon moves around the earth, but the sun doesn't. They basically move the exact same way. But he ended up publishing huge breakthrough and absolutely elegant model for the data they had at the time. Fit very well. Well, they ran into a problem because as we started collecting more and more data, even with this model, these planets weren't quite moving in circles around the sun. They didn't quite match our data. We were getting data that said when Mars was right here, a day later it should have been right here, but we were actually finding it, like right there, a little bit off.
Okay.
And we couldn't figure out what was going on. And so someone trying to be the next Copernicus says, I've got an idea. Not only are planets traveling around in circles, but they travel in circles as they go around in circles.
Which is spinning or not spinning?
Not spinning, but that they're
actually turn.
moving in a circle as they're moving in a circle. So the orbit, it's moving in a circle, but as it's moving in a circle, it's moving in a circle. So that its orbit would be something more complex.
That just made that way more complex.
Yeah, but it fit the data better. And if you started using this model, then Mars was right here, next it should have been right there, and it's kind of working. But as they collected more data, it stopped working again. And the next guy trying to be Copernicus said, I know. They're moving in circles, as they're moving in circles, as they're moving in circles. And they found the circles and circles and circles that fit the data. And they collected more data, and that broke down and it stopped working. And so eventually a guy by the name of Kepler comes along and says, each planet moves in an elliptical orbit with the sun at one of the focus of the ellipse.
Meaning?
Do you know what an ellipse is? You've done an ellipse in...
The eclipse, yes.
Did I say eclipse? I meant ellipse.
No, I'm
elliptical.
I know what an eclipse is. I don't know what ellipse is.
Your conic sections,
Huh?
your conic sections, a circle, an ellipse, a parabola, and a hyperbola.
I know the latter two.
You've never seen one of these before, an ellipse.
Just like an old.
Well, I mean,
So how is an ellipse constructed? You take 2 points, and then you pick some distance. And you take all the points where the sum of those two, if I pick some point here, let me just draw it. So using those as my foci, roughly freehanding it, my ellipse would look something like this. The property of an ellipse is the distance on there from each of the foci is always the same. So whatever this distance plus this distance is for that point is going to be the same as if we pick this point. That distance plus that distance. Those two distances will equal those two distances, and it will be the same two distances wherever we go.
Like, have you seen that thing where they have two nails and a string, and then they put the thing in and trace around?
Yeah, I don't know if we have a string in here that we could quickly use to construct a
What?
ellipse. But an ellipse.
yeah.
The equation of an ellipse that you should have seen, x squared over a squared plus y squared over b squared equals 1.
I mean, it looks. I don't know. It looks like math.
Looks like that. In the special case, so a is your distance from the center of the ellipse to its furthest point.
A's distance. Okay.
Here's a. B is that distance.
Yeah. So 2b is A.
No, not necessarily. Your ellipse could be stretched more. Here's another possible ellipse. With the foci like right here and right here. A would be your distance from the center to here. This would be your A. This would be your B. So A could be 4 times as big as your B.
So what's with the two dots?
A could be exactly equal to your B. Those are what we call your foci. They are used. The property an ellipse has is pick any point on the ellipse. Its distance from this point plus its distance from this point will always be the same. And those 2 points that you use are called your foci.
You're saying
The focus, that's a focus, and that's a focus.
Okay.
Just the name of the point.
Those 2
Foci.
points distance added are from that to the center.
the distance from here to the first foci and from here to the second one, that distance is going to be the same. Add the length of that line plus the length of that line. You're going to get some number, like we'll say 10 miles. Okay. Now pick this point. Measure its distance from here and from here. You're going to get 10 miles. Now pick this point. Measure its distance from here plus its distance from here. You're going to get 10 miles, or whatever it is. It's going to be a constant. Those are going to be the 2 points you measure from.
Yeah.
Okay. So, here's the equation of an ellipse. A special case of an ellipse is when A and B are equal. What happens when we go over this way as far as we go up this way?
It's a circle.
It's a circle. So if A is equal to B, call it R. Rewrite this equation. X squared over R squared plus Y squared over R squared. Multiply both sides by R and you get the equation of a circle, which you know and love. So a circle is a special case of an ellipse. It's where both the foci lie at the center.
Okay.
Alright, an ellipse. So, Kepler says, planets don't travel in circles and circles and circles and circles. They just travel in an ellipse. And how did he figure that out? The madman, just by staring at a bunch of data and figuring out that an ellipse fit the data.
And what? So why would it not be the same thing every year? Why would it not appear the same every year? Oh, because the Earth spins. Okay. I think I got it.
Okay, so realize planets are not traveling in circles. Planets are traveling in ellipses around the sun. And the sun is at one of the foci.
Yeah.
It's at a focus point.
It's and the Earth is in the middle, you said.
No, the Earth follows this path around the sun. It follows an elliptical path, not a circular path.
Okay.
Now it follows one really close to a circle. Notice that if A is really close to B, then that ellipse is almost a circle.
Sure.
And for most of the planets, their ellipse is very close to being a circle. It's a very circular ellipse.
Mm-hmm.
It has very low eccentricity, is what we call it, but now I realize you've never heard that either, and so you don't know how to calculate that.
Yes.
We'll calculate it once, and I'll tell you what it is, but for now, that's Kepler's first law. Planets do not travel in circles. They do not travel in circles and circles and circles. They travel in ellipses. So the planet moves in an elliptical orbit, not a circular orbit, an elliptical orbit, with the sun at one of the focus of the ellipse.
Okay.
Good so far?
Yeah.
That's what his first law says. His second law. A line from the sun to a given planet sweeps out equal areas in equal times.
Sweet.
What does this mean? Yeah, let me draw you a picture. So say we got a planet here. Here's my sun. Here's a planet on a super elliptical orbit. Let's say in 1 month, it goes from here to here.
Okay.
This is the area it swept out, that triangle.
Mm-hmm.
Let's say, fast forward in some other time, now the planet's over here, and in 1 month it goes from here to here.
The areas are.
And it sweeps out that amount of area. Kepler says this area and this area will always be the same.
For a month.
For a month, for the same amount of time. However much time the Earth sweeps, however much area the Earth sweeps out in 1 hour, that will be true in the next hour, and the hour after that, and the hour after that. And in 500 years from now,
Same thing.
look at the area that sweeps out 1 hour, it will be the same area. So, a line from the sun to a given planet sweeps out equal areas in equal times. Or in other words, here's the way we write that as the equation. We're saying that the way that that area is changing that you sweep out with respect to time is a constant. However much area it's sweeping out per second, it keeps sweeping out that same much per second. So the change in area with respect to time is always the same. It's always sweeping out the same amount of area per second.
Yeah.
If you think about that as the speed of your sweeping out area, it's a constant. Doesn't change for any given planet.
Yeah, makes sense.
Okay. Kepler's first law, the fact that planets travel in ellipses, this is not something we can prove. We can, but it'd just be extremely hard mathematics. So very difficult, but you can prove this from Newton's laws.
You'd have to find the two focal points, wouldn't you?
That's not even close to the hard part. The point is, it is possible to prove, using Newton's laws, that planets travel in ellipses. We will not do that derivation. It is a very messy, hairy, difficult derivation relative to us.
Okay.
But it is possible to do. You can prove it from Newton's laws. Remember, Newton comes after Kepler. So Kepler did not use Newton's laws to make this discovery. He just stared at data until it made sense in his head. Or whatever he did, I don't know. Newton coming after Kepler, when he was coming up with his laws, one of the things he needed to confirm was that planets travel in ellipses given my laws. And so that's one of the ways he tested his law of gravity. He says, does that law of gravity mean planets travel in ellipses? And that's one of the things he confirmed, and he did the derivation that we will not do.
These were co-linear, like they were at the same time. These two people.
Contemporary?
Yeah,
contemporary?
Sorry.
Kepler is older than Newton. Much older. Now, their lives likely overlap. I would bet good money that their lives overlap. But
So how did they come up? How did
Kepler
come
was
up-
famous when Newton was growing up.
How did Kepler come up with that without Newton's laws?
He stared at the data for a long time. A little bit about Kepler. Kepler is one of the strangest people you can come across. He was a weirdo who, if you remember from philosophy, this guy is a Pythagorean through and through. He is convinced that somehow numbers are real. He was very much a mystic that way, thinking that they actually exist in our universe somehow, like a Pythagorean would, and was convinced that there just had to be these elegant rules of nature to describe everything. And so he just went on the hunt, figuring out that there's got to be something. And he worked on it hard enough. He was also a smart guy, and he figured it out. But he's a crazy guy.
A genius. They're crazy.
He's a genius in one way,
They're crazy. Stupid. Yeah.
and then said a lot of nonsense in another way.
Yeah,
So, if you remember from philosophy, you can think about him a lot like a Pythagorean, and that's a pretty good thought. Okay, anyways. So, first law, can't be proved from Newton's laws, not a chance of us doing it. Second law, that the change in area with respect to time is a constant. That is, also, all these you can prove from Newton's laws. These are not laws in and of themselves anymore. Our laws now are Newton's laws, and these are now theorems of Newtonian mechanics, things you can prove. We will prove the second one. Okay? This one we can actually prove, and it's actually an easy proof, even though it seems like it might sound more complicated than that one.
it looks.
Yeah, on the surface it seems like that would be harder to prove, but turns out it's the easier one to prove. So let's go ahead and do that proof really quick. I'm going to prove that change in area with respect to time is a constant. That's what we're trying to prove.
Okay.
With me?
Yeah.
So first we need to get that little change in area. So I took this triangle here and I tried to blow it up and draw it there.
Okay.
We're going to call R the distance to wherever our object currently is as it's moving.
Okay.
Okay? We're just capturing the little triangle around where the object's moving.
VT.
The triangle that's going to sweep out with some amount of time.
What's your DS?
ds is,
Display.
so we're going to make this, I'm drawing this really big, but imagine this an infinitesimal little area, dA.
Oh.
I'm just drawing it big so that we can label stuff. You with me? So the area of this thing is going to be a dA. ds is going to be the little length of the base of our triangle as we take smaller and smaller triangles.
Which there is no base, but yeah.
What I'm trying to exaggerate here is that the base of the triangle we're using is not perfectly going to line up with the edge of the ellipse.
Yeah, that's what I was saying.
Okay, so that's why I drew it so big so that we could exaggerate that fact and you can see that. But in the limit, this triangle will perfectly capture the area of the ellipse over that little distance.
Going to zero.
Going to zero. As we make that smaller and smaller and smaller, we get better and better approximation.
Better, yeah.
Okay, so ds is going to be the base of our little triangle here. R, the distance, the length of our triangle, the height of our triangle, that's what I want to say. Theta here is the angle of your velocity. Now this isn't perfect circles anymore, so your movement is not going to be perfectly at a right angle with the radius anymore. It's going to be tilted a little. If it was always at a perfect right angle, you'd be traveling in a perfect circle.
Yeah.
So it's going to be tilted some away from a right angle.
Wouldn't that change
So-
the value of it too?
Change what?
The value of the velocity too?
Well, the velocity is just going to have two components. It's going to have the velocity that's going into the fact that you're turning off of a circular path, and then it's going to have the component of your velocity perpendicular to the radius.
Okay.
So you're going to have your velocity, here's your velocity, And then v perpendicular is the portion of your velocity at a perfect right angle.
Okay.
With me so far?
Yeah.
Okay, so now the area of this thing is what we're calling by dA. What is the area of that? It's a triangle.
So 1/2 base time.
1/2 base times height. Exactly what you were saying.
Mhm.
What is ds? It's r times d theta.
ds r times d theta. Yeah, changing. Okay. Yeah.
Your radius times your arbitrarily d theta being a.
Changing your angle.
Yeah,
That's
but I called that theta. Let's call this angle phi, because I'm calling, if this theta is the angle you're moving around at. So d theta is your small change in angle for this. So I shouldn't have called that theta,
Okay.
because theta is going to be over here as you're sweeping out.
Yeah.
Theta is how much you've swept out.
So that's v.
Okay, so we're going to call that phi. Has nothing to do with this d theta. D theta is a small change in angle by your really small triangle. With me?
Yeah.
Okay, so dA is equal to 1/2 base times height. ds is the same thing as r d theta. So that's going to give us 2 r's, which is our r squared d theta. You with me so far? So there's the area of one of those little infinitesimal triangles.
Yeah.
Okay, we're trying to prove that dA dt is a constant. So I was just figuring out what dA is. That's all we were doing so far. Now dA dt then, dA dt is going to be dA dt. Just put a dt in there.
d dt.
All right, now when theta is this angle that you're marking out, what is your change in theta with respect to time?
Displacement.
That's your angular speed. Your change in your
Oh,
angular
yeah.
position with respect to time is your angular speed.
Where's your position?
Theta is your angular position, what angle you're at.
Yeah, but okay, yeah.
So your change in your angular position with respect to time is how fast you're moving around it.
Yeah. Yeah.
Okay. So d theta dt is omega.
Yeah.
Now what is omega? Coming back over to circular motion.
V times r.
Well, v times r. V is equal to r times omega. When this is the v of uniform circular motion.
Oh, it's not.
We don't have uniform circular
Yeah.
motion. But if we just focus on the portion that's perpendicular, that is a portion of your velocity that is going into uniform circular motion,
Yeah.
if you want to think about it that way. So, r times omega there is the same thing as this v, the perpendicular v. Not your velocity, but your velocity perpendicular to your radius.
Yeah.
So that's what 1 r omega went into, and we still have an r there. You with me?
Mm-hmm.
Now, 1/2 r times your perpendicular velocity is the same thing as 1/2 r times v times the sine of phi.
Sine.
Take v, take the sine of this angle, and that gives you the y component, which is the same as that.
You're saying that's a right angle. That's.
This angle is phi. So drop that down to a right angle, making your
wow,
triangle.
what the heck?
The height of that is the same as your velocity perpendicular.
Wouldn't it? So if you cross your v to your v perpendicular, that'd be a right angle too.
Like that?
Yeah.
Yes.
Okay, that helps. Yeah.
Because it's the portion of v going straight up. That's what that is.
Straight up, and one's
Going perpendicular. What portion of our velocity v is going that way?
Yeah. Okay.
Take that angle, take the sine of the angle. It's v sine of that angle gives you that.
Which would be your
So v sine of theta, or sine of phi now. Theta's the angle over here. Sine of phi is your perpendicular velocity.
Yeah.
Now that's all I did. So I replaced v perpendicular with v sine of phi.
Isn't that cosine?
No. Cosine's this way.
Yeah.
Sine's this way.
Where's your angle measuring from? Oh,
Theta.
yeah. You're right.
Or phi, sorry, I keep calling it theta.
Yeah, that's right.
So there's my angle, here's my velocity.
So that's your sine.
The y component, the x component. The y component is v sine of phi.
Yeah.
Okay, that's all I did there. Okay, so notice dA dt, whatever it is equal to this quantity. All we are trying to do is prove that it's a constant. So I'm going to prove to you that this quantity is constant.
Okay.
And we're going to come at this from a very strange place. It turns out this is a consequence of angular momentum. So, put a pin in this equation. We'll come back to it. dA dt is equal to that. Put a pin in it. Let's remind ourselves of angular momentum, L.
Angular momentum.
Angular momentum. How do you get the magnitude of your angular momentum? You do the cross product of your position and your momentum. R crossed with momentum gives you angular momentum. The same way that R crossed with force gives you torque. R crossed with, that's just momentum, gives you angular momentum. Now, how do you find the magnitude of a cross product? You do the product of the two times the sine of the angle between them.
Product of the two times sine between them.
Yes.
Product of the two.
So if phi is the angle between them, then that's what it would be.
Okay.
Now notice, in our case, that's exactly what phi is. What direction is your momentum in? The same way as your velocity. And what's your radius?
Just
It's your radius. So the angle between your momentum and your radius is phi. Okay. So now what is L over 2m?
L is your.
Here's L. So what's L over 2m? Well, just take that and divide it by 2m.
Divided by 2 of your mass, which.
Mass is crossed out, and you get r times b times sine of theta over 2, which is the same as that.
Yep.
So notice that this is the same thing as L over 2m.
Okay.
Now, put a pin in that. And let's look at your change in angular momentum with respect to time. Change in momentum is a force. Change in angular momentum is torque. What is torque? It's the cross product of r and your force. How do you calculate that? That is going to be r times f times the sine of the angle between them. This time we'll call it alpha. What is the angle between our force of gravity and r?
Our force of gravity and R.
Which way is gravity pulling our object?
To R.
Right along r. Which way is r? Right along r. What's the angle between those two?
0.
0. What's the sign of 0?
1.
0.
0.
How high are you at 0 degrees?
0.
0. So this is all just 0. So what does this say? Our angular momentum, our change in angular momentum is 0.
So our torque is 0?
So our torque is 0, but in particular, our change in angular momentum is 0.
Oh.
If our
it's
angular
constant.
momentum isn't changing, then our angular momentum must be
Constant.
constant. And dA dt is related to our angular momentum. So dA dt can't be changing. So since angular momentum is conserved in this case, then it's sweeping out the same amount of area in the same amount of time. Very strange way for that to show up.
Yep.
But there it is, the way that conservation of angular momentum shows up in orbits that Kepler stumbled upon. Okay. That one I think is the most interesting of his 3 laws, but let's quickly do the third one. We'll read it here and then go over and talk about there. What does the third one say? The periods of the planets are proportional to the 3/2 power of the major axis lengths of the orbits, of their orbits.
The periods of the planets are proportional.
So he's coming up with, he's describing period, we have it written here, and he's essentially saying the relationship has a 3/2 power, but rather than radius, it's using the major axis, which is this distance.
Axis.
Major axis of an ellipse is this distance.
So I can.
This is the minor axis, this is the major axis of an ellipse. Sorry, it's very unfortunate that you don't have much experience with ellipses, so you don't know these terms.
Yeah. Okay. Yeah.
But he's basically saying that whatever your ellipse is, your period is going to be related to the distance the planet is away from the sun to 3/2 power. Remember, he's before Newton, so when Newton comes up with an equation for period, that's one of the ways he's going to confirm. Am I right? When Newton comes up with his laws, he needs to make sure Kepler's laws are still satisfied.
Okay. Yeah.
So we've already shown that Kepler's third law holds in the case of circular orbits. Oh, will you pull that table? Now, the consequence of this, so here's Kepler's version of a period now. So where A is half your major axis, A on an ellipse is, here's my ellipse,
Yeah.
that is your A.
A is not any acceleration. It's
No, in this case it's just that.
major axis length.
It's half your major axis.
Half your major axis.
2A is your major axis. 1A is half your major axis.
It makes
It's
sense.
your biggest radius, if you want to think about it that way.
Biggest radius. Okay.
Okay. So, Kepler says the period, how long it takes a planet to go around, is equal to 2 pi times a to the 3/2 all over mg,
Yeah.
under the radical.
He came up with that before Newton.
He came up with this before Newton. Newton confirmed this,
Through his laws.
so that his laws imply this. Now, he didn't have it written out exactly this way. Obviously, he can't use something like g before Newton comes along to even figure out what g is.
I wonder how he wrote that down.
He would have said t is equal to some constant times 2a to the 3/2. Now you can pull the 2 out,
Oh, yeah.
and then cos times cos is still constant. And so it's going to be equal to some other constant, call it c, times a to the 3/2. That's what he was saying, is it's proportional to that.
Yeah.
And whatever that constant is, he said is the same for all planets.
Okay.
Because 2 pi over the mass of the sun times g under the radical is the same for all planets.
Yeah.
So he said the cos is the same for all planets, and it's associated, if you just know the distance to the planet along its major axis, that's enough to figure out the period. So we just need to know how far away they are, and we can get the periods, or vice versa. If you know the periods, you can reverse engineer it to figure out how far away they are. Okay. Now, there's something astonishing about what this says. What does that mean? The period is just related to the furthest away the object gets from its center.
You're saying not necessarily the size of them, or
So, I've tried to draw, here's the sun, and I tried to draw the orbit of two different things. And I've tried to draw it so that the diameter of this is the same as the diameter of this ellipse, the major axis. According to Kepler's laws, this thing's orbit and this thing's orbit will take the exact same long.
it's a,
Because in a circle, A here is just R. So I drew out this ellipse so that A would be roughly that big, which I tried to make the same as the radius of the circle, R.
yeah, that's
And so,
impossible.
those two very different orbits, if I drew it somewhat accurately, have the same period. It takes the same long to go around.
Do they have the same speed?
Do they have the same speed? And the answer is no.
Well, then
The speed
that
of
makes
this
sense.
is much harder to talk about than the speed of this. This one is going in uniform circular motion. We have the equation of its velocity written up there.
Yeah. So, well, obviously, if they're different, that's why.
Well, now this one's velocity, you can't talk about its velocity because its velocity is always changing. Because now what's happening, as this comes closer and closer to the sun, it speeds up, speeds up, speeds up, speeds up, it reaches its max speed here. And then as it goes away, it slows down, slows down, slows down, slows down, reaches its minimum speed here. Because it's getting closer and further away from the sun, you can think about that the same way as me throwing this up in the air.
Yeah.
The higher it gets, the more it slows down. The lower it gets, the faster it goes.
That's all acceleration then.
Yeah, so this thing accelerates and then deaccelerates, and accelerates and deaccelerates. So it speeds up and slows down all the time.
Okay.
Whereas circular orbit is just one velocity. So very different.
It makes sense. It makes sense.
Okay, so let's talk a little bit about Halley's Comet. So Halley's Comet, as it goes around, here I've drawn the sun. So there's the sun. Halley's Comet path, drew it very roughly here. It's perihelion. This is its distance when it's closest to the sun. So its perihelion is this distance from here to here. here's the path it takes. So when it's closest to the sun, that distance is 8.75 times 10 to the 7 kilometers. Its aphelion, when it's furthest from the sun, that's this point. At that point, it is 5.26 times 10 to the 9 kilometers. So it gets pretty close to the sun and then way further away. It's like 100 times further away here than it is right here. So my picture's not even close to accurate.
Yeah, it would be way over.
Good so far?
Yeah.
Okay. So now, our job is first to find A. What is A in this case? Not acceleration. They mean the semi-major axis.
Yeah, the shortest or longest.
Right. So the entire major axis will just be the perihelion plus the aphelion. And that would give me this total distance. You see that?
Yeah.
So if I call this one R1 and this one R2, then 2A is just R1 plus R2.
Yeah.
And then you can quickly find A. A is just equal to R1 plus R2 all over 2. With me? Okay. Next, they want us to find the eccentricity of the ellipse. Now, this is something that you would have learned in an algebra course, but apparently not.
Yeah.
So the eccentricity is what portion of A over is our focus.
What percent?
Yeah, what percent?
Okay, what?
If it was halfway over, E would be 0.5.
Yeah.
If it was 2/3 over, E would be 67%.
And it's 3.
If it was 0 over, E would be 0 and you'd have a perfect circle. So a circle has 0 eccentricity. You can't have 100% eccentricity because you can't get the focus on the edge of the ellipse.
Okay.
Okay. So, with that, our job is find the eccentricity. So I know that this distance is my eccentricity times A.
Yeah.
And that has to be equal to A minus R1. And that leaves me E of A, or E times A.
That makes sense.
Divide both sides by A gives me the eccentricity. So let's get these values really quick now. So let me see. I will do 8.75 times 10 to the 7. And I will store you in X. And I will do 5.26 times 10 to the 9. And I will store you in Y. So R1 for me is X, R2 for me is Y. So, really quick, we'll find our A here. Then our A is just going to be X plus Y divided by 2. And we get A is equal to 2.67 times 10 to the 9. 2.67 times 10 to the 9 kilometers. Because everything's in kilometers, right?
Yeah.
Which, because this number is so much smaller than that number, our average is basically just going to be half of that number. So that makes perfect sense.
Yeah.
Okay, next, let's look at, now that we have our A, let's look for our eccentricity. Our eccentricity, what are we going to do? We're going to do A minus, did I do that as X or Y? Guess we'll find out if it comes out positive or negative. Divided by A. And we got eccentricity of 97%. So if I drew this correctly, I'd have to have it 97% of the way over. So Halley's comet gets really close to the sun and is super far away.
97 is insane.
Yeah, so if I tried to draw one that's a little bit more accurate, it would probably be something more like this. With the sun right there.
Dang, that's insane.
So
How does it even come back? You're saying it doesn't ever reach escape velocity?
No, because it's orbiting.
What? Dang, that is insane.
Okay, yeah, so there's Halley's comet.
Is that a real comet or a real thing?
Yes. Oh, last thing we need to calculate is its period. Let's calculate its period now. To calculate its period, I really quick need to convert A to meters. That way it comes out in seconds. So take A, multiply it by, because I have A in kilometers right now, right? So multiply it by 1,000 gets me meters. Okay, so now I need to do, we'll just really quick story in x. Okay, so now I need to do 2 times pi times a to the 3/2 all divided by the square root of, I don't have the mass of the sun off the top of my head. Sugar.
I'll figure it out quick if you need.
Yeah, Google it real quick. I think I might have it written up here somewhere, but maybe you can find it before I find it. I swear I wrote it. Oh, I have it right here. Mass of sun. 1.99 times 10 to the 30 times g.
Are you in nano kg? Non-million? Oh.
Okay, so that is seconds. Divide by 3,600 gets me to hours. Divided by 24 gets me to days. Divided by 365.25 gets me to years. And that is coming out to 75.5 years.
You divide by 365?
T is roughly 75.5 years. Really quick, Google Halley's Comet, period. Just ask really quick if it'll say it. You try it that way. I'll try seeing if I can find the problem where we did it. $75.5 years. Okay. So there we go. We found the period of Halley's Comet. Comes around once every 75.5 years.
Holy.
When did the last come around?
1986.
1986. Well, there we go. So probably live to see it.
Like 6 times.
Be sad if you don't.
It was 1500. We're gonna see it again. Well, you might not. We will.
All right.
2020.
Now we're done talking about death. Let's move on now to our big derivation. Oh my goodness, it's 3:20.
Spherical mass distribution.
Yes. So one of the things that we have been assuming this entire time is that when you are a mass outside of a sphere, you can pretend that all the gravitational force is happening at its center of mass.
Which is not the case.
It is the case, and we need to prove it's the case.
Wait, it's not the case.
It is a valid assumption. And so that is what I'm going to prove here. So I am going to show you, here's what I have. Here's you.
Oh,
Here's the Earth.
No, it's not the case.
It is the case. Here's you. Here's the Earth. I'm going to calculate your potential energy relative to the Earth, and I'm going to prove to you that it comes out to negative your mass times the mass of the Earth times g divided by r, which is what it would be if all the Earth's mass were just right there at its center of mass.
Yeah, but the only thing you're assuming is we are measured by a point too, a particle.
Well, you're just somewhere up in space. Oh yes, we are assuming you're a particle.
So not in reality, but in.
Yes, you are a particle relative to the Earth.
Okay, then that makes sense.
But it also works for two spherical objects too. But we'll handle just this case.
Super.
So here's you, here's the sphere of the Earth. We are going to prove that your potential energy relative to the Earth is given by this equation.
Okay.
How am I going to do this? I am first going to calculate the potential energy given by one spherical shell around the Earth. Okay? So that's actually what our picture is here. This is an empty spherical shell. Very thin little shell around the Earth. And we're going to calculate the potential energy from just this shell.
Okay.
Okay? So I'm going to use m sub s for the mass of just this shell. And r is going to be the radius of just this shell.
Okay.
And the way that I'm going to calculate the potential energy now of just this shell is I am going to take a bunch of little slices of these frustrums all the way down and calculate it from each one of the frustrums.
The frustrum is what?
It's
That.
sliced in that, but it's all the same height. Okay. So, du, the potential energy from just this little slice of frustum going around the surface here, going around the shell there, is going to be equal to m times whatever mass this thing has, which is dm. It's going to have some infinitesimal mass. And there is your mass, whatever that is. That's just going to be a constant throughout this whole problem. So dm there is the mass of just this little slice of that surface of a shell. dm times g, our constant,
Yeah.
divided by s. S is your distance from here to that surface.
So just radius, basically.
No. It's s, not r. R is your distance from the
Yeah.
center of the Earth.
It's just how you think.
S is your distance to wherever we took that slice. S is going to change because I'm going to take the slice here, 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 here. I'm going to do infinitely many slices and add them all up.
Yeah,
So S is constantly changing. But since we're just doing one shell at a time, all this ring going all the way around, it's your distance from M to it is S is going to be the same all the way around. So now this is a valid equation because your distance to all the mass is S.
the same.
To every little piece of mass in that ring going around. You with me so far?
Yeah.
That's why we can use this equation so far. So that gives me the potential energy you have from just this little slice. I need to add up all infinitely many slices to get it for the shell, and then add up all infinitely many shells to get it for the sphere. So starting by getting all the slices to get it for just the shell. That's what we got to do first. So here it is, du. Now, what is our, what's our problem? Our problem so far is we have a dm, but what changes as we take each slice?
Your S.
Your s. So I need somehow a ds in there if I'm going to integrate with respect to s. And I have a dm. So we got to start by working with that.
Okay.
And I'm going to use our relationship between the areas to make my substitution.
Oh, so what we already did over there.
So what is the area? What is this area of this frustum?
0, approaching 0.
It's going to be, if you draw it to the side here. Sorry, that's not a very good drawing. Because it's circular. And it comes down. Curves. Whatever. So if I go down to the middle of it, then it's going to have some radius r. So going around the whole frustum is going to have radius 2 pi r, and then I need to multiply that by the length here. And that will give me the area going around.
Isn't that length virtually 0?
What length? This length?
Yeah.
No.
So what's 0?
It's whatever that length is. Let's call it s in this case. Then the surface area is just 2 pi r times s.
So what's thin thing are you cutting?
Oh, over here, ds goes to 0.
That's what
Oh, sorry. But this is just some random frustum. And you
No,
actually want
not
to calculate
that.
this area. Well, just start with some frustum. You take an actual piece of paper
Okay,
folded
so
that
yeah,
way.
okay, it's
There's its area. Okay, so now the area of one of these things, a dA,
It's going to be 0.
is going to be 2 pi r. R here now is the radius of the frustum. What's this thing's radius? It's not this r.
Yeah, it's
It's r sine of theta, where that's theta.
r sine of theta.
Yes, so for the radius from
yeah.
here to here,
Yeah, I see.
here's r, here's theta, that distance
That's
is
the
r sine of theta. Okay, so that's our radius, so 2 pi, the radius of the frustum, times ds. ds is the same thing as r d theta.
Okay.
Good so far?
Yep.
So dA, now combine my terms, we have an r and an r there, gives us an r squared, and so here it is so far. There's our dA, the area of that little strip. Now, the area of our little strip divided by our total area of the whole sphere has to be equal to the mass of our little strip divided by the mass of the whole shell.
Okay.
Because the mass, we're assuming the mass is uniformly distributed.
Yeah.
So whatever portion of area that is relative to the whole thing's the whole shell's area is whatever a portion that mass is relative to the whole shell's mass. So dm over the mass of the shell is equal to dA over the area of the shell.
Yeah, that makes sense.
And now, coming back up here, remember our problem was we need to substitute dm and somehow get ds in there.
Yeah.
So we can use this, now solve for dm by putting ms over there. And so we get dm, oh sorry, before we do that, let's just rewrite dA over A. So coming over here, what is dA? We just figured it out, that's right here. What is the surface area of a sphere? 4 pi r squared. So dm over the mass of the shell is equal to the area of just that strip over the area of the whole shell. What is the area of just that strip? That's what we figured out right there. What is the area of the whole shell? 4 pi r squared.
Where's your ds?
Sorry, we're getting there.
Okay.
I jumped ahead thinking that we were ready for the substitution. Okay, now notice over here what cancels. Pi cancels with pi, r squared cancels with r squared, 2 and 4 cancel, leaving a 2 in the denominator. And so you're left with dm over